So here we have gravel falling on a conical pile. So we imagine a cone, and gravel is falling on there, and as it falls, it all trickles down and slowly makes that cone bigger and bigger and bigger. So you've got some sort of conveyor belt here. The gravel's going up and getting dropped on top of this pile, and that conveyor belt is able to put that gravel on there so that you're putting 4 meters cubed on there per hour. So every hour another 4 meters cubed gets added to this. In this case, my diameter right here is always double my height. So my drawing is not really very good at this moment, but that is the relation, that's the size of cone it is. So your diameter is always double your height. We want to find the rate of change of the height. So what we're trying to find is dh dt, which means that height is a function of time at the moment that the height is 3 meters. We're told how much the cone's volume is changing. The cone's volume dV dt is changing at 4 meters cubed per hour. So when the height is 3 meters, how fast is that height changing if you're constantly putting gravel onto this? So again, the way to start, we need to have some sort of equation that involves height and involves volume. And the idea being here, we know it's a cone. Do we have a volume formula for the cone? The volume formula for a cone, yes. Whew, I know. Okay. In the cone formula, you have the cylinder formula. Cylinder formula is pi r squared times height. That's an easy formula, I think, to remember, because if you imagine a cylinder, there's a circle at the bottom, there's a circle at the top. Volume is how much space something covers. So if you took a piece of paper and cut out a circle and put that on the bottom, then took another piece of paper that was a circle and kept cutting them out all the way up, you'd eventually fill that whole cylinder. And that cylinder would be a bunch of circles, pi r squared. How many would you have? Well, however high it is, that's times your height, and that'll fill your volume. A cone is much smaller than a cylinder, but it has the same base. It just goes to a certain point at the top. It happens to be that the volume of a cone is 1/3 of the volume of a cylinder. I don't have a good visual for you to think why it's 1/3. Best thing I would do is buy an ice cream cone that was the same size of a cup that you have, pour water into your ice cream cone and pour it into the cup. It'll probably come up 1/3 of the way. I don't know, the more crazy examples you can imagine for it, the better chances are you're going to remember the formula. So, there's our volume formula. Notice that our volume formula has volume, radius, and height. What do we want to find? We want to find dH dt. We know dV dt, but we also have an r in here. And we don't know dr dt. We don't know how much the radius is changing with respect to time. So we have to do a little bit extra work here in order to change this equation so it just has volume and height. In order to do that, we're going to need to replace the radius with an expression that's just in terms of height. Is there any way that we know a relationship between the radius and the height? Yeah, we know that the diameter is equal to 2 times the height. Radius is half of the diameter. So if the radius is half the diameter, is it okay that if I say that 2 radius is equal to 1 diameter? If I do that, I can substitute into this equation, and that says that 2 radiuses equals 2 heights. So in this case, that means that my radius and my height are identical. If my diameter is double my height, my radius will be equal to my height. So now I can take this formula and replace the r squareds, the r with h, and then I'll have h squared times h, which will become h cubed. So now I've written a formula just with the volume and height. Right, because this r will be h, and h squared times h will be h cubed. Now we can do the derivative with respect to time of both sides. And this side will just get dv dt. Here the derivative will be pi h squared, the 3 and the 1/3 will cancel out, times by dh dt. And when the height is 3 meters, we know that our volume is changing at a rate of 4 meters cubed per hour. Our height at 3 meters when it's squared will be 9. So solving for dh dt, divide both sides by 9 pi. .141. Height is measured in meters, time is measured in hours, meters per hour. So this cone is getting taller and taller by about 14 centimeters every hour. So even though you're putting a lot of volume onto that cone every hour, that height isn't increasing too much. Of course, as time goes on, that height will slow down. So you'll be able to, sort of realize, if you're in your office and you're looking at the gravel getting added on and it's getting closer and closer to the top of the conveyor belt, and if it gets to the top, you could run into some problems because you can't go out there and shut it off. Instead of just running out there and shutting it off, you take out your calculus, you calculate how fast it's increasing. You're like, oh, I still got another 25 seconds before I have to run out there to shut the machine off. Okay, that kind of idea. Perfect question for Winnipeg in the middle of April, especially this year. Snow is melting. Should have melted a month ago, but that's okay. Finally, we get temperatures where it's warm enough that things can melt. So we got a snowball in a perfect sphere because you really like making it nice. And you just set it out there, and it's just hovering in space so that it can melt perfectly in a sphere. And it's melting so fast that it's decreasing. Its volume is decreasing at 1 centimeter cubed per minute, which isn't very fast. If you want to visualize how much 1 centimeter cubed is, that's 1 milliliter of water. So every minute, only 1 mil of water drips off of this snowball. So probably the temperature outside is like 1 degree or 2 degrees. Not very hot because it's melting pretty slowly. When the radius gets to 5 centimeters on this snowball, so it's a pretty big snowball to begin with, how fast is that radius decreasing? So again, we've got a sphere. We want to find, we're asked to find how fast a radius is decreasing, so we know that radius is a function of time. We're given how fast the volume is changing, so we know that volume is a function of time. Can we figure out a formula? Do you know the formula for the volume of a sphere? That's the surface area. There it is. 4/3 pi r cubed. Which is a really cool formula because of calculus, and we'll talk about it in a second. So there's your volume formula, 4/3 pi r cubed. I was going to talk about it. I'm going to talk about it now. Okay? Something very cool about the volume of a sphere. Take the derivative. dv dr. Let's just do dv. Let's just do the regular derivative. What do you get? The derivative of the volume is the area. And not just a coincidence. It's very cool. It's like one dimension down, just like you can go from distance to velocity to acceleration. You can go from volumes to areas. Very cool. Very cool. Anyways, there's probably some really cool YouTube videos about why the derivative of volume is a surface area. You should probably look that up and spend the rest of your evening watching math videos. That would make me happy. Anyway, so that's a very cool thing. But we're not going to take dv dr. We're going to find out what happens with respect to time of both of these. So we're going to do the derivative with respect to time of this side and the derivative with respect to time of this side, and we get dv dt equals, well, we get the 4 pi r squared times dr dt. We know that this is changing at a rate of 1 centimeter per minute. At the moment that the radius is 5, what's dr dt? Divide both sides by 100 pi. Radius is measured in centimeters. Time was measured in minutes. So it really gives you a sense that it's not very warm out if that radius is only changing 0.003 centimeters every minute. So you could really sit there and watch that snowball slowly melt for hours and hours and hours.